All right, we're going to get started here with 3.8 now, and this is going to be in two videos where we're going to do the first one where we talk about derivatives of inverse functions, and then the next video will be where we talk about logarithmic functions. All right, so let's start here. Just speaking, I should probably start on the first page. Here we go. Given a function's graph, the graph of its inverse is reflected over the line y equals x. Okay, so hopefully you remember that. That's this line right here. You see it, it's right there. It's this red dotted line. And then if we have these two functions that are inverses of each other, the 1/2 x and the 2x minus 2, if you look in the picture, you can see it's like they're just like you took that red dotted line and folded across it, and then this part would line up with this part, and this part would line up with this part if we folded along that dotted line. Okay, so that is a property of them. Now, let's calculate the derivatives of each of these functions. So let's start with f prime of x, the first function here, this one. If we take the derivative of that, we have d dx of 1/2 x plus 1, and then we take the derivative of 1/2 x, that just gives us a 1/2, and the derivative of 1 is 0. So we get f prime of x equals 1/2. Now let's do the derivative of the inverse function, this one over here. And the way you write this is you write the inverse function like that, put parentheses around it, then put your prime symbol, then write your x like that. And so this is the derivative of 2x minus 2. And if we take that derivative, the derivative of 2x is 2, the derivative of minus 2 is 0. And so the f inverse prime of x is 2. And so what do you notice about these? How are they related to each other? Hopefully at this point you're just noticing they're reciprocals. Okay, they're reciprocals. So let's go ahead and talk generally about this. Okay, those were just two straight lines where the slope was the same along the whole way. So no matter what, everywhere the slopes are reciprocals. But what you have to notice is that, and I'm actually going to try and squeeze two things in here. You have to notice that b is f of a, right? If you look in this graph, b is f of a. So this is the point AB, and or something, and A is f inverse of B. All right. So when we're not comparing slopes at the same point, we're comparing slopes at corresponding points, because essentially, because of that reflection across the line, across this, right? Here's our y equals x. We end up with this blue line like this. And where the slopes will match up is when, instead of being BA, this is going to be like this. This will be A. This is B, like in this picture over here. And these two slopes, I know I didn't draw it very well, are going to be reciprocals of each other. All right, so you have to be very careful with that. I'll get that off of there because that's a big mess here. Okay, so you have to be very careful with that. So the derivative of the inverse at AB is the reciprocal of the derivative of the inverse at BA. So you have to swap the points. And here's one I want you to think about. What happens if we have a horizontal tangent? All right, if we have a function of the horizontal tangent and you try to do its inverse, what are you going to get? Draw yourself a picture. Think of what happens when you invert the function of a horizontal line, and see what you get. So think about that one, and you should be able to figure that out. But I want you to think a little bit about that question. All right. So here's the theorem, theorem 3, and it's the derivative rule for inverses. If f has an interval I as domain, and f prime of x exists and is never 0 on I, then f inverse is differentiable at every point in its domain, the range of f. The value of f inverse prime at a point B in the domain of f inverse is the reciprocal value of f prime at the point A equals f inverse of b. Basically what this is saying is, if we wanted to write this maybe a little differently, it is just what we said on the previous page. If you have the derivative of a function, then you can find the derivative of its inverse by essentially doing this. Like if we wanted, I know I've been doing a's and b's, but maybe this will make it a little clearer for you. If we wanted the derivative of the inverse, right, and we wanted to evaluate it at a certain point, like x equals b, then essentially what you're going to do to get that is you're going to do 1 over f prime of whatever the y value was, of the corresponding one. You got to swap them, if that makes sense. You have to figure out what it is in that in reciprocal base and do it from there. So you're kind of just swapping what the x's and y's are, because x's and y's swap when you do inverses. So let's try using it. Let's look here. So we have the function f of x equals x squared, and we have its inverse, f inverse of x equals the square root of x. All right, and we're going to find the derivative of both of these. So f prime of x, that's the first one here we're finding, is just going to be, from here is just 2x. Bring that exponent down and subtract 1, right, when x is greater than 0. So now the derivative of the inverse, f inverse prime of x, remember this is x to the 1/2. So we bring the 1/2 down and then we subtract 1, okay? Which makes this 1 over 2 root x. 1/2 power is a square root, and the negative exponent means reciprocal. So there we go. So those are our two derivative functions, okay? So let's look at part C. Part C says, find f prime of 2. Theorem 3 gives a method for finding this with specific values. So what you need to note here is, what we're going to do is essentially we have to plug back in this 2 back up here for x. All right, so if we do f prime of 2, right, let's think of it this way. If we do f prime of 2, that's using this right here. That's 2 times 2, that's a 4, okay? But if we want to verify our theorem, we should then find f inverse prime of not 2, oops, I wrote an equal sign, not of 2, but of 2 squared, from plugging it back up in here. Because essentially, if we're saying that a equals 2, what does b equal? Well, b is going to equal 4. And so if this is true for the point 2, 4, this down here has to be true for the point 4, 2. Okay? We have to flip-flop them. So we're actually going to look at the inverse function's derivative at 4, not at 2. It's not because of this 4. Okay, don't think that. It's because of this 4 up here that comes from the original function when we plug that in, right? This was x, this was y, and we swapped them. So we have to look at 4, which means this is 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1 over 4. And there you go. They are inverses of each other at those points. Okay? So let's take another look at one more example here. And then I think we're done with this section. So let f of x equal x to the third minus 3x squared minus 1 whenever x is greater than or equal to 2. Find the value of the derivative of the inverse function at the point x equals -1 equals f of 3. So if we're actually taking our original function we're looking at, this is like saying this is a, this is saying this is b, because we're actually plugging this in to our original function. If you look back here, this is what a was. A was the value that we plugged into the original function to then get b. And so if we're plugging in 3, that's a, we're plugging into the original function, and then we get what we're going to have to plug into the inverse. So we can do this without even finding the inverse of the actual function. All we need to do is find the derivative of the function f prime of x is 3x squared minus 6x, and then the derivative of negative 1 is just 0. And then what we can do is do this. We want to find the inverse derivative at x equals negative 1. Well, that means it's, according to the theorem, f inverse prime of b equals 1 over f prime of the inverse value. So essentially it's going to be f prime of 3. Okay? Because remember what we were doing back here on this is we were doing 1 over the regular derivative evaluated at x equals the inverse of that. So that's what we have here. 1 over the derivative evaluated at 3, because that's what we have over here, what we have to plug in. All right, so when we do this, we get 1 over 3 times 3 squared minus 6 times 3. Okay? And sorry, just to clarify this just a little more, just to make sure you realize this, what I'm saying is if f of 3 equals negative 1, then f inverse of negative 1 equals 3, right? So this was supposed to be 1 over f prime of f inverse of, sorry, this should be a f inverse of b, like that. Okay, so really this came before that step, but that's what I'm saying. That's why it's f of that. And so it becomes, sorry, just trying to make this a little clearer. That's why this becomes f inverse of negative 1 is equal to 1 over f prime of 3, like that. Okay, because f inverse of negative 1, which is the b, is 3. All right, so I just wanted to clarify that. I don't know, I started thinking that maybe I wasn't super clear there. So anyway, if it doesn't make sense, be sure to just ask me about it. So let's take a look here. So this is 1 over that. 3 squared is 9. 9 times 3 is 27. And then 6 times 3 is 18. And 27 minus 18 is 9, so 1/9. And there's our answer. We didn't have to actually find the inverse of the function. We just simply had to find the derivative of that and then find what it was plugged in. Okay, that's pretty much it for this first part. The next video will probably be just a little longer, but it's about derivatives of logarithms and natural logarithms, dealing with exponentials and stuff. Okay, so that's it for now.